Okay, so this is Chapter 6, Lesson 2, and last time we spent time talking about important terminology in this unit. We were talking about the system and the surroundings, and we were talking about work, and we're going to continue with that now, but we're going to focus more on how this relates to chemical reactions. We're going to start talking about internal energy and state functions. We're going to talk about enthalpy, and we're going to talk about heats of reaction. So we're going to talk about internal energy and state functions. A state function is a property of a system that depends only on its condition or state at that present time. You don't have to write that down, it's on the next page. So here you can see that whether we take 50 grams of ice at 0 degrees Celsius and we heat it, or we take 50 grams of liquid water at 100 degrees and we cool it, that the internal energy is the same, 50 grams of water at 25 degrees, regardless of the pathway or state that it took to get to that final destination. Another way I can explain this is the altitude of a plane isn't going to change from point A to point B regardless of the path that it took to get there. So that change in altitude is going to be constant. But the path that the plane takes to get to that destination is going to vary. So let's look at two examples of the real world, so to speak. Sweat, evaporating, can happen in two different ways. In the first case, we look at the sweat as the system, and the surroundings is your body and the universe. So in this situation, Q, or heat, is going to be greater than 0. Why? Because heat flows into the system, meaning sweat, from your body in order to raise the kinetic energy of the sweat molecules to allow them to go from the liquid phase to the gas phase. So that's one situation. In situation 2, you are the system, and the surroundings is the sweat and the universe. In this case, Q is going to be less than 0 because heat is flowing out of the system, meaning you, into the sweat and the surroundings. Since heat leaves your body, this cools you down. And that's exactly what happens. Here's yet another example. You have a parking garage. The altitude at the ground level, state 1, and the altitude at the top floor of the garage, state 2. That represents some change in altitude. Now, whether I drive my little car up and around each floor to get to the top, or whether I take my car and I put it on the elevator to get to the top. That change in altitude is going to be the same. Therefore, that change in altitude is analogous to a state function, because that change in altitude is independent of the path taken. Whether I take the long road and drive around each floor, or I take the car elevator. Okay, let's get to a definition. So, property of a system that depends only on its present state. Okay, an example. I'll go back to my plane. You're the pilot of a plane. You're leaving Chicago at 596 feet, and you're flying to Denver, Colorado, where it's 5,280 feet. So your change in altitude is equal to 4,684 feet. The path that you took to fly there is independent of that altitude change. So what are some variables that are state functions? Well, energy, temperature, and pressure. Variables that are not state functions would be heat and work. Okay, so in this diagram, we're looking at the changes in energy. So you have potential energy stored in the bonds of products as compared to the potential energy in the bonds of the reactants. When we break bonds, we absorb energy, and when we make bonds, we release energy. So you can see what's happening here when you take ethane and you form carbon dioxide and water. So you're making new bonds, so you are releasing energy. The same thing is happening over here. Well, actually first, when you take ethane and you break it down into ethene, okay, you need energy to do that. So you're absorbing 136.2 kilojoules. We can then take that ethene and we can also, through combustion, break it down into carbon dioxide and water and hydrogen gas, and that's going to also be exothermic. You're releasing energy because you're making new bonds. And then again, in a third step, where you're just breaking down CO2, water, and hydrogen gas, we're also releasing a little bit more energy. So honestly, this is just showing you that when bonds are broken, energy is absorbed, and when bonds are formed, energy is released. So in the example of the combustion of octane, octane is C8H18 plus O2 yields CO2 and water. So this is a liquid, this is a gas. So this is going to be 8, 9, and we'll talk about this in another unit, 25 halves O2. So in this reaction, because I'm just showing 1 mole of octane, okay, delta H is equal to negative 5,460 kilojoules. So when we talk about heats of formation, which is yet another term, we're talking about 1 mole of the substance. So here 1 mole of octane is going to release a lot of energy. And this is why we consider it an extensive property, because it depends on the amount of reactants. Which means you can predict already that stoichiometry is going to come into this unit, because I'm not starting with 1 mole of something. I need to be able to calculate the energy for whatever the given amount of reactant is. So reflecting back on an earlier equation, remember that this is delta E equals Q plus W, where delta E is the change in internal energy. Q is heat, and W is work. So I just want to bring this up because we can change, okay, or internal energy, right, can be changed. How? By changing, right, by changing the flow of work heat, or both. All right, so let's talk about enthalpy now. Enthalpy is the heat absorbed or released under constant force and pressure. We don't have to write force because that's implied by pressure. Now, enthalpy is going to be an extensive property. It's going to depend on the amount of reactants used. Since energy, pressure, and volume are all state functions, then H, or enthalpy, is also considered a state function. Now, I'm not going to go through the whole equation manipulation here, but I want you to see page, in my book it's 253, and it goes through the breakdown of this equation. And you get a final equation of delta H is equal to delta E plus P times the change in volume, because pressure is constant. Now, one thing that we have to remember in a reaction is the delta H in a reaction is going to be equal in magnitude but opposite in sign for a reverse reaction. So if the forward reaction is positive delta H, the reverse reaction is going to be negative delta H. But the magnitude, the value of that is going to be the same. Another way that we can look at this, just to introduce something else, is specifically in a reaction, your delta H of your reaction is going to equal the H final minus H initial. Okay? So remember, it's like that parking garage, okay? The change in the altitude is always going to be the same regardless of the pathway taken. We're applying that to a reaction now. The change in enthalpy of a reaction is going to be your final state minus your initial state. All right, we have a few more terms to make sure that we go over before we start doing some problem solving. So endothermic is energy absorbed. It's characterized by a positive delta H. And you're going to have a positive heat, and you're going to have a positive work. Why? Because the energy of the system is increasing. Okay. Clearly, exothermic is the opposite of that. We have energy released. It's characterized by negative delta H. Our Q is going to be negative. Our W is going to be negative. And the overall energy of the system is decreasing. And if you recall from Regents chemistry, activation energy is the minimum energy to initiate a chemical reaction. And we're going to talk about that right now. Okay, so this slide did not copy correctly into explain everything, so I had to doctor it up a little bit here. So as we just said, activation energy is the minimum energy to initiate a chemical reaction. So here you have a bulldozer that's trying to push this rock, okay? And in order for this rock to continue down the hill, it's got to climb to here. So this is our activation energy, the amount of energy needed to get this reaction started. Now, if you notice, this looks like a potential energy diagram. To review a couple of things from last year, remember that from the baseline to here is the potential energy of the reactants. Okay? And from the baseline to here is our potential energy of the products. My line is a little off here. We'll move this up. On yours it should line up. So the change in the potential energy of the products and the potential energy of the reactants gives us our overall change in energy. And we referred to this as delta H, or heat of reaction. So let's move from our bulldozer and rock analogy to an actual reaction. So here we can see that we have H2O. This is actually going to be water being broken down into hydrogen gas and oxygen gas. Okay, so water being broken down. Here we can see that this is an endothermic reaction for two reasons. One, we know that when we break bonds, energy has to be absorbed. We can also look at our delta H, which is going to be positive because the products are higher than the reactants, and it's always the energy of the final state minus the energy of the initial state. And we have our activation energy, the amount of energy needed to get from the reactant line to the top of the hill. I want you to notice the activation energy in this reaction. And then let's compare it to the next slide. Here we have the opposite. We have the formation of water. So we have the formation of water from hydrogen gas and oxygen gas. And this is an exothermic reaction. We're making bonds. Therefore, it's going to have a negative delta H because the products are lower than the reactants, and it's always the final state minus the initial state. And notice the activation energy. The activation energy is almost half of what it was in the previous slide, which means that it's going to take a lot less energy to get this reaction going than the previous one. So most reactions take place at constant pressure, and the change in volume is nearly zero. So in these cases, your delta E is equivalent to your delta H. There are four things, though, to remember when dealing with enthalpy. The first one being your delta H, or your heat of reaction, is the energy of the products minus the energy of the reactants. P always comes before R in the alphabet. Enthalpy is an extensive property. Therefore, it depends on the amount of the reactants. Your delta H for a reaction is equal in magnitude, meaning value, or quantity, but opposite in sign for the reverse reaction. And delta H for a reaction depends on the state of the products and reactants. And when we say state, we're talking about liquid, gas, or solid. Okay, so let's take all of that prior knowledge, all of the terminology, all of the background information that we've learned, and now apply it to a practical purpose, problem solving. So let's look at this reaction. Nitrogen gas and oxygen gas form dinitrogen monoxide. And in the process, 163.2 kilojoules of energy is absorbed. How do I know that it's absorbed? Because I have a positive delta H, which tells me that my reaction is endothermic. They now want us to calculate the amount of heat transferred when 12.8 grams of dinitrogen monoxide forms at a constant pressure. So we're back to stoichiometry. Stoichiometry is the foundation of everything. That and knowing how to write compounds and how to write reactions and balance them. So I'm starting with 12.8 grams of N2O. And we know that 1 mole of anything is equal to the gram formula mass. In this case, 44 grams of N2O. And in this case, we know that 2 moles of N2O absorbs 163.2 kilojoules. So 2 moles of N2O absorb 163.2 kilojoules. My grams cancel, my moles cancel, and I'm left with 23.7 kilojoules. I wrote kilograms here. Okay, that should make sense. intuitively, because 2 moles produce 163, or absorb 163.2 kilojoules, okay? And we're only dealing with 12.8 grams, which is a lot less than a mole. So this again proves that delta H is an extensive property because it depends on the amount of reactant. In the next one, how many grams of N2 must react to produce a delta H of 1 kilojoule? Only 1 kilojoule. So we're starting with 1 kilojoule. We know from our reaction that 163.2 kilojoules is what's absorbed when we have 2 moles of N2O. And 2 moles of N2O come from 2N2. And we know that 1 mole of N2 has a mass of 28 grams. So my kilojoules cancel, my moles of N2O cancel, my moles of N2 cancel, and when I do the math on this, you can see that you can cross out 2's even. I'm going to cross out this 2 and this 2. So 2 times 28 divided by 163.2 is going to give me, I don't know where to put the answer here, 0.343 grams. 0.343 grams. Again, that should make sense because 2 moles was equivalent to the absorption of 163.2 kilojoules. Now I only want to absorb 1 kilojoule. It's got to be a very small amount of mass. Again, this whole thing demonstrates that energy is being transferred from the surroundings to the system. Why? Because it is absorbing energy. Okay, let's look at another example here. Hydrogen peroxide can decompose to form water and oxygen. Water and oxygen. I don't know why when it comes in to explain everything, it will not take the arrows from the PowerPoint. It's like so weird. All right. Calculate the value of Q when 5 grams of hydrogen peroxide decomposes at a constant pressure. All right, so we have hydrogen peroxide decomposing and H2O and O2 are formed. Now notice that this is a negative 196 kilojoules, which tells us that it's exothermic, predominantly. Yes, there was some energy going in to break the bonds in the H2O2, but the formation of the new bonds of the water and the oxygen gas release energy. So the reaction is predominantly exothermic. So we're starting with 5 grams of H2O2, and we know that 1 mole of H2O2 approximately has a mass of 34 grams. I'm rounding here just for instruction. What do we also know? We also know that when we have 2 moles of H2O2, that this much energy is released. So we're going to use that as a conversion factor. So we have 2 H2O2 and negative 196 kilojoules. So our grams cancel, our moles cancel, and when we do the math on this, we have negative 14.4 kilojoules. Which should make sense because 5 grams is much less than 68 grams, which would be equivalent to 2 moles. Okay. So the Hindenburg disaster. I put this link as a separate link in an update. If you have time, take a look at the video. It's kind of cool. I cannot play it within Explain Everything because there's like copyright issues, and then YouTube will take the video down. So I'm listing it separately. So here we have hydrogen gas and oxygen gas, and we're going to form water. So negative 484 kilojoules. In this example, and this is exothermic, which makes sense because combustion is releasing a whole lot of energy. If I have 7,062,000 cubic feet of hydrogen gas at STP, how much energy produces how much energy given 1 cubic foot contains 28.3 liters of H2 gas? So let me rephrase that because that's kind of awkwardly written the way they have it. They want to know how much energy is produced by 7,062,000 cubic feet of hydrogen, given the conversion factor that 1 cubic foot equals 28.3 liters of hydrogen gas. Now, you know that 1 mole of anything equals the gram formula mass. You know that 1 mole also equals 6.02 times 10 to the 23rd atoms or molecules. There's also one other mole equivalent, which is 1 mole equals 22.4 liters of a gas. So that is going to be relevant in solving this problem. So I'm going to move this up a little so that I can solve it down here. So we've got 7,062,000 cubic feet. And you know that 1 cubic foot is equal to 28.3 liters. I just told you that 1 mole equals 22.4 liters of a gas. And in our equation, we know that 2 moles releases 484 kilojoules. So 2 moles of H2, negative 484 kilojoules. So if cubic feet cancel, liters cancel, moles cancel. Voila. I do the math. I get a very large number. And it would be 2.16 billion kilojoules. That is a lot of energy. Okay, winding down, just 3 more examples. I want to make sure that you have enough examples. All right, oxygen may be generated on small scales in the laboratory by the thermal decomposition of potassium chlorate. So we've got KClO3, solid, which breaks down into KCl, solid, and O2 gas. So let's balance this. Okay. Delta H is negative 89.4 kilojoules. This tells us that it's exo. And in this reaction, they want you to calculate the delta H for the formation of 6.45 grams of oxygen. So here is our oxygen. So how much energy will be released when I only form 6.45 grams of oxygen gas as opposed to 3 moles of oxygen gas? All right, so I'm starting with my 6.45 grams of O2. You know that 1 mole of O2 has a mass of approximately 32 grams. And in our equation, you know that when you have 3 moles of O2, that releases negative 89.4 kilojoules. So this cancels. We do the math, and we get negative 6.01 kilojoules. Sweet and easy. Now, the next one. This is where the remedial reading comes in. For this reaction, calculate the delta H for the formation of 9.22 grams of potassium chlorate. So I'm forming potassium chlorate. Therefore, it is the reverse reaction. Remember, the magnitude is the same, but the sign is opposite in the reverse reaction. So for this one, I need to use positive 89.4 kilojoules. So I'm starting with 9.22 grams of KClO3. I know that 1 mole has a gram formula mass of approximately 122.5 grams. And I know that 2 moles of KClO3 is going to be positive 89.4 kilojoules. So my grams cancel, my moles cancel. I do the math, and I get a positive 3.36 kilojoules. I'm giving you a variety of problems so that you can be attuned to what you need to look for in the problem-solving process. Okay, which of the following has the highest enthalpy at a given temperature and pressure? H2O solid versus H2O liquid versus H2O gas. Well, first of all, it takes energy to convert something from a solid to a gas. Therefore, solid has the lowest enthalpy. You know, as you go from a solid to a liquid to a gas, energy is absorbed. When you hold an ice cube in your hand, it melts. Why? Energy is absorbed. So, that being said, you know that H2O gas is going to be less than H2O liquid, which is going to be less than H2O solid. Let's look at an example. H2 gas plus 1/2 O2. Remember I said it's the formation of 1 mole when we look at the energy values. Has a delta H of negative 286 kilojoules. And H2O gas, H2 gas plus O2 gas, H2O gas, is going to be negative 242 kilojoules. The differences in the change in energy reflects the difference in the energy content between a gas and a liquid. When we talk about the delta H for 1 mole of a substance being formed, there is a list in the back of the book that you're going to be using in this unit, I believe, to look up the different values. And you would be given that on an exam. You'd be given a sheet, or it would be right in the problem. Okay, last slide. When solutions containing silver ions and chloride ions are mixed, silver chloride precipitates. Your delta H is negative 65.5 kilojoules. So they want us to do three things here. They want us to calculate the delta H for the formation of 0.2 moles of silver chloride from this reaction. Well, obviously you know 1 mole releases 65.5 kilojoules. So 0.2 moles is going to be considerably less. Okay? So that's the intuitive portion of it. So let me move this up a little bit, and we'll start to solve down here. So number 1, we're starting with 0.2 moles of AgCl, right? And you know that 1 mole of AgCl releases negative 65.5 kilojoules, or releases 65.5 kilojoules. These cancel. You're going to get negative 13.1 kilojoules. Short, sweet, to the point. Next one. Calculate delta H for the formation of 2.5 grams of AgCl. Well, again, you know that your delta H is going to be very small because 2.5 grams of AgCl is a whole lot less than 1 mole. And from the balanced equation, we know that 1 mole is negative 65.5. So let's look at this one. So 2.5 grams of AgCl. You know that 1 mole of AgCl has a gram formula mass of 143.5 grams. And you know from the equation that 1 mole releases negative 65.5 kilojoules. So grams cancel, moles cancel. I do the math on this, and I get negative 1.14 kilojoules. Again, just using stoichiometry, and now we're using the mole and energy value as a conversion factor. In the last problem, calculate delta H when 0.35 moles of AgCl dissolves in water. Well, let's think about this one. Our reaction is representative of aqueous silver ions and chloride ions forming the precipitate. Now they want us to take the precipitate and dissolve it in water, which is going to be very difficult because it forms a precipitate, but let's go with the flow. So now in this reaction, we are using the reverse, which means that our delta H is going to be positive 65.5 kilojoules. So we're starting with 0.350 moles of AgCl, and we know that 1 mole of AgCl is positive 65.5 kilojoules. Moles cancel. I do the math, and I get positive 22.9 kilojoules. So in order for this to happen, the reaction has to absorb 22.9 kilojoules of energy from its surroundings. It's got to pull it into the system in order to make that happen. Okay. Now you're set to go do the problem set. No pun intended.